We now analyze another example or another circuit, so this particular circuit in here. And in this case, I also have an input, a single input X and a single output Y, but in this time, I made X actually appear in the output, and that will change the diagram a little bit as you will see shortly. So let's get started with that. Again, I have only a couple of flip-flops in here, A and B, so I'm going to start with the state equations. So the state equation here for A, the next value of A, or the next value of flip-flop A is actually AT plus 1. Well, it depends on whatever I have here. Again, I'm just going to highlight what equation I'm writing. I'm writing the equation that actually is in here and here. So this one here, you can just follow that. This is just B. And X in here, it's actually just, this is a Q bar of A. So it's A bar. So this one here is A, the current value of A bar, and then the current value of B, and then the current value of X. And that's the state equation for A. I can do the same thing for B. So for B, you will see that it's actually just a couple of AND gates and whatnot. So we're going to have to figure out what's here. This is just B prime, X prime. Okay, so let me just write that. It's actually B bar or prime and X bar. And then the circuit in here, it's actually just whatever I have in here, which is A bar, X bar, which is plus A bar, X bar. And that's the state equations for A and B. And of course, I have to write the output equation for Y. And in this particular case, Y is, I believe it's B bar, A, and then X. And I'll just rearrange it so that it's A, B followed by X. So all I have to do is just say A, B bar, and then X. And that's the state equation for this particular circuit. So the next step usually is I'll copy, or actually I don't have to copy it. I can just read it or leave it here. All I have to do is just fill the state table. So in the state table in here, I'll have to fill that state table with a bunch of zeros and ones. Okay, that's a 0, that's a 1, that's a 1. Okay, so based on the next state here, so I'm going to start with flip-flop number A. So whenever X is 0, the next state will be 0. So that will be 0, 0, 0, 0. So whatever X is 1, well, it depends on A and B. So A should be 0 and B should be 1. So I'm looking for 0, 1, which is here. And the rest of them should be just a bunch of zeros. All right, and that basically now finishes flip-flop A. For flip-flop B in here, I'm going to take a look at this particular circuit. Well, this one here is, I can just start with, I believe whenever X prime, whenever you have, well, let's do that. So it's A prime, X prime. So I'm looking for 0 in here and 0 in here. That's, well, sorry. It's 0 in here and 0 in here. Okay, so I'm looking for whatever A is 0 and X is 0. So that is here and here. And now this will be 0, this will be 0. The same goes in B0 in here. Actually, let me just do that here. Let me just do that. So when X is 0, okay, and it happened, well, I'm looking for X is 0 and B is 0. So I'm looking for this guy in here and this guy in here, which is that. So I'll have to have a 1 and then a 0. And of course, this one here is telling me it's X and 1. If X and 1, that will be 1 not as 0, and this one not as 0, that's a 0 or 0, so all of them should be zeros, and that's how we do it. So now here's the difference from the previous example. In the previous example, we only have output Y, but now I have X equals 0 and X equals 1 because X appears in the output. It actually, X is the input, appears in the output directly without actually going through the flip. Well, it affects the flip-flop, but it also appears directly into Y. All right, so let's see how would that affect it. Well, I'm looking for a pattern of 0, or actually 1, 0, 1. So I'm looking for, well, I'm looking for 1 followed by a 0 when X is 1. So anything when X is 0, it's just 0. So I'm looking for 1 followed by 0. And I think that's the one in here. So that's 1, 0, and 0, and 0. And now that's the state, or the state table. So now I can take that state table and I can, for example, say, well, this is my state 0, this is my state 1, this is my state 2, and this is my state 3. And I can just from there go and write my state diagram. So how to write the state diagram? Well, first I'm going to say, well, I have a circle that's basically S0, and I have another circle in here. I'm going to say that this is S1, and I have S2, and I have S3. Okay, and now all I have to do is just read that state table to figure out. So whenever I'm in 0, the next state will be either 1 or 0 based on value of X. So if X is 0, it happened to move to state number 1. Okay, I usually do that. Okay, and when X is 1, it will stay in the same place in here. So now I can go to state 1 and figure out what happens. So it either stays in the same location if x is 0, or it usually moves to state number 2 if x is 1. So I'm reading this one here now. So this one tells me the next state is going to be either 1 or 0. So it's either 1 when x is 0 or 0 when x is actually 1. And now I can see this last state in here. It's actually the only way we can do that. It actually goes here, whether I have the input 0 or the input 1, the next state is there. And there's no way, technically, if you think about it, this S3, it doesn't seem to be a reachable state. So if you actually start from S0, there's no any arrow coming into it. And you can see from the next state in here, I don't see a 1, 1 anywhere. So technically this S it seems to be unused, but for this particular case, for the sake of completion, it seems to be whoever designed the circuit decided, which I designed it in such a way that actually it goes to 0, 0 just in case. But anyway, so that's how this particular circuit works. However, we still have to indicate where the outputs are. We're going to do this here. So these outputs will depend on the input. And now, because they depend on the input, in the previous example, we said like we're going to write it inside the state names, basically the circles that indicate the states. In this particular case, it's not, because it actually is affected by x. So this x here affects it. All right, so how do I go about it? Well, we're going to have to see, well, technically the only way we can get a 1 is actually whenever I'm currently in state 2, which is this one here, and the input is 1. So technically all I have to do is just say /1. This is the only time when I will actually get a 1 on the output. Usually the output is indicated on the arrows if the input actually appears in the state equation for the output in here, or you see the input directly affecting the output with a combination circuit and without any flip-flops, like basically directly. All right, so we usually indicate it on the transition arrows. And this is an example of what we call a melee machine. And again, we're going to get to the differences between a melee or a Moore machine in a separate video. But for now, all we have to do is just indicate the outputs, and you can just go technically for every arrow, you can see I'm writing a 0. However, this isn't always the case in every circuit. It's going to be a little bit different. And generally speaking, I just didn't want to confuse you, but whenever I actually go through a row and I figure out what the next state is, I also indicate the output right away. But anyway, so that's what the state diagram is telling me. So all I have to do right now is just try to analyze it. And technically, if we're starting from S0, this particular circuit is looking for a pattern of 0. So I can just write, well, S1 seems to be memorizing that 0 has happened. And you can see this here emphasized. So if 0 happens, that's it. So you stay in the same state, in the same state, in the same state. Next, you will see that actually whenever 1 happens, you move to S2. Okay, so S2 is just memorizing 0 followed by a 1. That's what's happening in here. And you can see that now, if I actually get a 0, I'm going to go back in here because S1 remembers a 0. However, if I get a 1, I'm going to go back in here and I'm going to reset all over again. S0 just remembers a 1. That's very similar to what we've seen before. But the difference now is the following. If I'm in state 2, the minute you get an input that is in x equals 1, which is here, you will see that it's transitioning to x0 and the output will be 1. So there is no S3 that is actually memorizing 0, 1, 1. There's nothing like this time. Actually, S3 doesn't seem to be reachable, so I actually don't know what we can technically just erase it completely and it will be fine. I'll be able to interpret the circuit correctly. However, it seems to be that whenever I designed it, I made sure that if for some reason or another you got into S3, you're going to go back to a reset state or somehow. But anyway, what is the purpose of this particular circuit? Well, it seems to be detecting a sequence of 0 in the input, followed by a 1, followed by a 1. So it is a 0, 1, 1 sequence detector. That is very similar to the example one that we've seen.